Hello everyone. So let's look at some more questions on acids and bases and how to do calculations regarding pH and equilibrium concentrations. So in this specific example, we're told that the solution of acetic acid is 11% ionized at 25 degrees Celsius. And then we're told to calculate the pH of the solution and the mass of acetic acid dissolved to yield 1 liter of the solution. We're then also given the Ka for acetic acid. So our first step is to just recall, what does percentage ionization actually mean? So percentage ionization, we must recall that it gives us the amount of hydronium at equilibrium divided by the initial amount of the acid, in this case acetic acid, multiplied by 100, and we're told that this is 11% for this acid. So and this is actually giving us a ratio of the two things that we need to calculate, because we're interested in the pH, which is of course linked to the amount of hydronium at equilibrium, and we're also interested in the mass of acetic acid, and that is of course linked to the initial amount of acetic acid that we need to dissolve to make up this solution. So we're going to find that useful probably at some stage. Now, the only way to determine equilibrium concentrations is by using an ICE table. So I've gone ahead and drawn out the ICE table for us, and of course we're looking at acetic acid. So acetic acid will react with water to form an equilibrium with the acetate anion and hydronium. Because it's an acid, it protonates the water, forming hydronium. So in terms of what happens here, if we dissolve some acetic acid in water, initially you should have some sort of concentration of acetic acid, right? Some concentration. Water does not have a concentration, so it's not applicable to it. And initially there shouldn't be any of your ions because the acid hasn't yet ionized. The change that you expect, so in other words, how does the system proceed towards equilibrium? Well, you expect your reactants to decrease in concentration and your products to increase in concentration, right? As per the reaction quotient, logical sense, meaning reactants need to decrease in concentration, and hence the forward reaction is favored. And as always, the water concentration is not affected. So hence, at equilibrium, we should expect to see whatever our initial concentration of acetic acid was should be less by X. Water is not applicable for it. And our product concentrations should be X. All right. And then typically, how do we calculate these values? So these values at equilibrium. Well, we use the Ka expression, right? So we say we were given Ka, so we can just plug it into Ka. We say Ka is equal to 1.8 times 10 to the negative 5. We use our equilibrium concentrations and we took them as XX and whatnot. But now what is X? Well, X is also the hydronium ion concentration at equilibrium. And we can turn to, because the problem here is now, typically we would have had the initial concentration, right? We would typically have the initial concentration. We would have said, yes, let's do the approximation and let's solve for X and whatever, and then get the pH. But now the problem is we don't have the initial concentration, nor do we have the pH so that we can get the hydronium ion concentration. But what we are given is the percentage ionization. So let's see what we can do from that. If we solve here for this ratio, so hydronium ion at equilibrium divided by initial concentration of the acid, we find that it's 11 over 100, so it's 0.11. And I mean, if you take this to the other side, all right, so let's rewrite it a bit more for ourselves. That means that the hydronium ion concentration is actually equal to 0.11 times the initial concentration of our acid, which makes sense because that's literally what it means. It means 11% of our acid is hydronium ion. That's what percentage ionization means. It means 11% of the original acid becomes hydronium. So let's put this into our expression, because this value, the hydronium ion at equilibrium, is X, right? It's this parameter that you put in the table over there. So let's plug it in, or let's substitute it in. So where there's an X, we put 0.11 concentration of CH3 CO2H naught. That's a square. And then this one is CH3 CO2H naught minus 0.11 concentration of CH3 CO2H naught. All right, top one, that is just a number squared, so that's 0.0121, and then it's this concentration squared. And the bottom part is, remember, it's two variables minus each other, but it's the same variable. So it's 1 times the concentration minus 0.11 times the concentration. So that means it's technically 0.89 times the concentration. It's the same as having an expression saying x minus 0.11 x, right? Then you would have said it's 0.89x. Okay, and now because we have the same thing here at the bottom and the top, we can actually cancel those two things, right? And then we're just left with 0.0121 divided by 0.89 times the initial concentration of our acid. And let's just remind ourselves what this is all equal to, Ka, which is 1.8 times 10 to the negative 5. Just write that a bit better. So we can solve this for the initial concentration, CH3 CO2H initial. I got a value of 1.323 and some numbers times 10 to the negative 3 molar. All right, and that's one of the things that we can use to answer one of our questions, because we're asked what is the mass of acetic acid dissolved to yield 1 liter. We have the concentration, we have the volume. So now we can get the number of mole, and from the number of mole we can get the mass. All right, and I went ahead and wrote that out. So first we get the number of mole of acetic acid, that is equal to 1.323 mole, right? Because molar is mole per liter. So, and from the number of moles, we can get the mass using the molar mass. So, depending on your periodic table, you might be out a little bit here or there, but I eventually get 0.080 gram of acetic acid is what we need to dissolve to get that concentration, initial concentration of acetic acid. Okay, so now our final step is to determine the pH of the solution. And to determine the pH, we of course need to determine the concentration of hydronium. And we have an expression to calculate the concentration of hydronium. It is equal to 0.11 times the initial concentration of the acid. And the initial concentration of the acid, we just calculated, right, as 1.323 times 10 to the negative 3. So plug that into our expression, then we have the concentration of hydronium. Right, here we go. There we calculate it. So now we know what the concentration of hydronium is at equilibrium. Right, and that is X. And once we have the concentration of hydronium, we can calculate the pH using negative log of the concentration of hydronium. And that is rounded to 2 decimal places because of the Ka being to two significant figures, 1.8. So I get 3.84. It makes sense. This is an acid. This is an acidic pH. It's less than 7. And this is round about the pH of acetic acid. You can Google that. And you'll see that it's round about the pH of acetic acid. All right. Cool. Thank you for watching. I hope this was informative. And a good exercise once again in that we actually have two unknowns but use something completely different to then solve for both of those unknowns. And a little bit more tricky algebra, just to keep you awake and have you work with some different things. Alright, thank you for watching. I'll see you in the next video.